So now we know the field due to a circular loop of wire, if we're looking at a point right in the centre of it. Now we're going to work out the field at a point somewhere near a long straight wire. We assume it's essentially infinitely long, and again it's carrying a current I. So once more we divide it up into segments ds. This time the segments of course are not all an equal distance away from P, but we have done a very similar thing for electric fields, so let's work through that now. So we start with our wire that is very long with a current I flowing through it. And we're going to talk about a point P here, and we're interested in the field at that point. So we'll start with a little segment, ds, and that is a vector that's pointing upwards. So we have a distance from that segment to the point, and we'll call that distance r. Now we'll let the closest distance be capital R, but little r will depend on which segment of wire we're talking about. So basically the distance s from the closest point to that little segment. And we're interested in the tiny amount of field dB caused by the current in this little segment of wire, and we'll say that the angle between the current segment at that point and the direction from the segment to the point, we'll say that angle is theta. Now, Biot Savart tells us that dB is mu naught over 4 pi I times ds cross r over r squared. Now we get the direction from the right-hand rule, so we're really interested in the magnitude. And the magnitude is mu naught over 4 pi I ds sine theta over r squared. Now we assume the wire is infinitely long. So our total field will be the integral from minus infinity to infinity of dB, and that will equal 2 times the integral from 0 to infinity. So we're going from 0 to infinity, and that is dB. So just by symmetry, the field due to half the wire will equal the field due to the other half of the wire. So that will be mu naught I over 2 pi integral 0 to infinity sine theta over r squared times ds. So all the constants have come out the front there. What we're left with is sine theta and r squared. Now both of those depend on the position of ds. So we need to get them in terms of this distance s, which is the distance of that segment from the 0 point. So let's just do a quick close-up of this. We've got capital R and we've got the point P, and this is little r, and that is s. Now that is theta. So that means this angle inside is 180 minus theta, but in our radians, that is pi minus theta. So we can say that r, which is the hypotenuse, is the square root of s squared plus r squared. And we can say that sine theta, which is actually the same by the rules of trigonometry, that actually equals sine of pi minus theta, and sine of pi minus theta is the opposite over the hypotenuse, which is r over square root of s squared plus r squared. So putting those things together, constants out the front, integral from 0 to infinity we have sine theta is r over square root of s squared plus r squared, and r squared itself is s squared plus r squared. So we end up with r at the top. At the bottom, it's s squared plus r squared times square root of s squared plus r squared, which gives us s squared plus r squared to the 3 over 2 times ds. So we'll continue over the page. So this is our integral, and to solve it we're going to cheat and look up a table of integrals that tell us that if we have a quantity that is x squared plus a squared, where a is a constant, to the 3 over 2, and we want the integral dx of that, it is just x over a squared times x squared plus a squared to the 1/2. So let's apply that to our integral, and now we have 0 to infinity r ds over s squared plus r squared to the 3 over 2 will equal r times, because r is the constant, we'll take that out the front, s over r squared, s squared plus r squared to the 1/2 from 0 to infinity. So that, with our r over r squared coming out the front, 1 over r times s over s squared plus r squared to the 1/2 from 0 to infinity. So let's look at what happens as s approaches infinity. S is now a lot bigger than r, so s squared plus r squared approaches just s squared. Then we have s squared to the 1/2 at the bottom there, which becomes s. So then we have s over s, which is 1. So that quantity in the brackets equals 1 at infinity. Now, if s is 0, we get s over something, 0 over r. So that's just 0. So we end up with b equals mu naught I over 2 pi times 1 over r times 1 minus 0 equals mu naught I over 2 pi times r. So that is the expression for the magnetic field due to a long straight wire, a distance capital R away from the wire, if it has a current I flowing through it.